Hello everyone, welcome to this course Digital Electronics and Circuits, and in this lecture we will talk about a method for circuit realization and circuit minimization which is called Quine McCluskey method. We have already talked through a method called K-maps. We have had two lectures on that where we looked at K-maps for circuit realization and minimization, and we saw how effective K-map was for giving us a circuit and reducing the number of product of sums, right? But the problem with K-map is it's difficult to visualize for 6 variables and above, right? So basically what we saw was for 3 variables we were able to draw a 2 by 4 matrix and we were able to solve it perfectly fine. For 4 variable we were able to add 4 cross 4 matrix, and solving this was fine as well, right? We were able to look at adjacent entries and form squares. For 5 variables it will be like 2 raised to power 5 possible combinations, 32 entries. This would be like overlapping to 4 by 4 K maps, right? This is still under control because we are able to overlap this. But for 6 variables, we will have 64 possible combination, and we have to overlap 4 K maps separately, 4 by 4, right? So basically, if we see if the number of variables increase, K maps are difficult to visualize. And one more thing, right? This particular technique of overlapping variables is not software adaptable. So for this, right, looking at such cases, we will use a new technique called Quine McCluskey method. And what we will do is we will look at this method while I explain you like how it works, and we will take a live example to take a look at it, right? So let's assume we have a circuit called or a function called f of abcd, which is equal to, we have 4 variables, which is equal to summation of 0, 1, 2, 5, 6, 7, 8, 9, 10, and 14. And let's assume that we have to create a circuit and we have to minimize the circuit using a Quine McCluskey method, correct? How do we go about it? The very first step for a Quine McCluskey method is, right, we will group minterms based upon number of ones in the minterms, based upon number of ones, right? And what we do is once we group them, let's create multiple groups. So basically in this particular case we will have a group 0, let's say, where there are number of ones being are 0. So how many entries will reside in this group? So there will be a grouping of say 0, 0, 0, 0. Correct? Let's put a name of group 1, and this group 1 will have all the terms which has at least which have exactly one digit as 1. So this will comprise of 0, 0, 0, 1. So 0 is done, 1 is done, 2 will also have 1, 1 only, 5 will have 2 ones, 6 will have 2, 7 will have 3, 8 will have 1, 1, 9 will have 2, 10 will have, okay, so 10 will have, 8 will have, 9 will have 2, 10 will have 2, 14 will have 3. So now let's go to group 2 where we have 2 ones. So 0, 1, 2 is done, 5 has 2 ones, 6 has 2 ones, 7 has 3 ones, 9 has 2 ones, right? And 10 has 2 ones. 9 and 10 are done. And remaining 7 and 14 has 3 number of ones. 7 and then we have 14. This is group 3. This is nothing but 0, 1, 2, 8, 5, 6, 9, 10, 7 and 14. Now what we have done is we have created number of groups, different groups depending upon number of ones present in the groups. Correct? Now what we have to do is, what we will do, we will compare group 0 with group 1, and we will look for terms which has only one differences. For example, when I say we will compare columns like rows in group 0 and group 1, what we would say is like, okay, let's assume this is our beginning 1, this is our second set of iteration. What we will do over here is we will compare group 0 entries with all the entries of group 1 and try to get numbers where only one min terms differ. So basically if we compare 0 and 1, right, so three digits are same and last digit is different. This is how we denote it. Correct? Now we will compare 0 to 2. Similarly, in 0 to 2, three digits are same, only one digit differs. Correct? 0 and 2. 0, 0, like this. Similarly, 0 and 8 also we have a similar scenario where we say 0 and 8. Three digits are same, one differs. Right? Now, does it make sense to compare group 0 with group 2 and group 3, right? We have already compared group 0 with group 1. But does it make sense to compare group 0 with group 2? No, it does not make any sense, because if you see, right, in group 0 and group 2, at least there will be two terms will be different, because this has only 0 ones, this has 2 ones. And basically, as we have seen in K-maps method as well, we combine the ones which are adjacent to each other. We don't combine the ones which are like far away from each other, right? So now our group 0 and group 1 is compared. We don't comparing group 0 and 2 does not make any sense. Same is the case with group 0 and group 3. So in our next iteration, right, what we will do is we will combine group 1 and 2. So basically when I say 1 and 2, can we combine 1 and 5? Yes, we can, right? And when we combine 1 and 5, what we will get? We will get first digit being a 0, then being a variable change, then 0 and 1. Correct? Similarly, we will combine 1 with 6. If we compare 1 with 6, is only one digit different? No, multiple digits are different. Similarly, so 6 is something which is left out right now. We will okay, 2 and 8 were done previously. Oh, if we combine 2 and 1 and 5 is be possible. 1 and 6, there is no more than one terms change. 1 and 9, we can combine 1 and 9 as well, because only one term differs. So we can put like this, right? 1 and 10, does 1 and 10 more than one digit differ, right? So 1 and 10 is also not possible. So we have done 1 and 9 also, correct? Let's go to 2. 2 and 5, no, more than one digit differ, right? So we can't do 2 and 5. How about 2 and 6? We can do 2 and we can combine 2 and 6, because exactly the second bit differ, rest everything is same, right? So 2 and 6 will be something like 0 hyphen 1 0. How about 2 and 9? 2 and 9. So we have more than one digit which is different. So 2 and 9 doesn't form a combination. 2 and 10. 2 and 10, yes, they form a combination with first digit between different. Correct? Let's go to 8. Does 8 and 2 and 10 are done, right? So 10 is also done. 8 and 5. Does they make a combination? No, they don't make a combination, because more than one digit differ. Similarly, 8 and 6 don't form any combination. 8 and 9, they do form a combination. If we combine 8 and 9, we will get, okay, let's make it a bit clearer, right? If we do 8 and 9, we will have something like 100 blank. Correct? 8 and 10, yes. Again, 8 and 10 also form a combination with 10 hyphen 0, right? Similarly, now we 1 and 3 make grouping 1 and 3 does not make any sense at all, because at least two digits are differ from if we go from 1 to 3. So now let's try to group 2 and 3, right? So once we try to group 2 and 3, what would happen in such a case? Does 5 and 7 form a combination? Yes, it does form a combination, right? If I say 5 and 7, what will be the case? 0, 1, hyphen 1. So 7 is also covered. 5 and 14 makes a combination. It does not make a combination, because more than one digit are different. How about 6 and 7? It does form a combination, which is 0, 1, 1, hyphen. How about 6 and 14? it again forms a combination which is nothing but hyphen 110. 14 is also covered, right? Do we have 9 and 7? No. 9 and 14? No. 10 and 7? Again, no. 10 and 14? Yes, we do have a combination for 10 and 14, and the combination is 1 hyphen 10. Correct? Now we have completed the first step of a Quine McCluskey method. All the minterms in column number 1, right? All the minterms in column number 1 over here, they have a corresponding, they have been compared with the corresponding different groups within column 1 we have compared, right? Now what we can do is, now we will divide column 2 into two different parts, right? So how do we end up dividing column number into two different parts? To do that, right, let's pick up a new color. So what we will do over here is, we have a column 2 from, see, basically one grouping was of 0 and 1, so we have these three entries. Then our 1 and 2 groupings, we had these many entries, and then we had a grouping of column group 2 and 3 within column 1, right? Now we will do the same iteration process and form a new column called column number 3. Okay, here we will compare group number 0 to group number 1 of column 2, right? So basically it's like comparing 0, 1 and 1, 5. Do they have any comparison together? Do they have any entries in common? They have entries in common, but they have only two entries in common. So basically, since they have only two entries in column, that we can't combine both of them. Then how about 0, 1, 1, 9? Can we combine them? Again, we can't combine them because they have more than one differences. How about 0, 1 and 2 and 6? Can we combine them? No. How about 0, 1 and 2, 0? Can we combine them? Again, no. How about 0, 1 and 8, 9? Right? 0, 1 and 8, 9 we can combine because eventually they have three items which are same. So what we will do, we will put something like 0, 1, 8, 9, and if you compare 0, 1 and 8, 9, so we can put this entry is different, right? 0, 1 and 8, 9, 0, 0, hyphen. So 0, 1 is done, 8, 9 is done, correct? How about 0, 1 and 8, 10? Not possible. Then similarly, if we iterate 0, 2 and 1, 5, not, no, we don't have only one item which is different. There more than one digits are different. 0, 2 and 1, 9. Similarly, we have more than one differences. 0, 2, 2, 6, more than one. 0, 2, 2, 10, more than one. 0, 2, 8, 9, more than one. 0, 2, 8, 10. We have a scenario where we say that, okay, 0, 2 and 8, 10. If we combine, we have something like hash 0, right? So we have covered 0, 2 and 8, 10 as well. Moving ahead, right? 0, 8 with 1, 5, nothing. 0, 8 with 1, 9. We have a combination of 0, 8 with 1, 9, where what we say is this 0, 0, this. Correct? Similarly, 0, 8, 2, 0. Again, we have one combination of 0, 8, 2, 0. 0, 8, 2, 0. Where we can say hash 0, hash 0. So 1, 9 is done, 2, 0 is also done, right? How about 0, 8, 8, 10? Nothing. Now once this is done, right, we will move on to the next group, right? So for that, since we are moving on to next group, let's change the ink color to something like, say, right now, this is one group we had. Now let's compare 1, 5 and 5, 7. Do we have any combinations? No. 1, 5, 6, 7, no. 1, 5, 6, 14, no. 1, 5, 10, 14, no. Similarly, 1, 9, 5, 7, nothing. 6, 7, nothing. 6, 14, nothing. Now if we go right next, if we move to 2, 6, there is a combination of 2, 6 and 10, 14, where we have hash 1, 0. basically what we will say is 2 6 is done, 10 14 is also covered once, right? Now if we then we have one more combination over here, which is 210 and 614 hash hash 10 way. So 210 is there and 614 is also covered, right? So we can mark 614 also as. How about any other combination? We don't have any other combination, right? Now, if you see over here, in between group 3, within group 3, no more combinations are possible because we don't have any entries which differ only by 1. They differ by more than 1. Correct? So, no more combinations are possible further. And what we can do is, if you see the number of repeated entries in column 3, for example, 0189 is same as 0819. So we can remove this, we can eliminate the duplicates. Similarly, 0280 is duplicate of 1. Similarly, this is also a duplicate, so we can remove a duplicate entry, right? So what we did, just to reiterate the steps, right? First, the number one step was we grouped minterms based upon number of ones in the term. We created multiple groups in the increasing order of number of ones. Group 0 had 0 ones, group 1 had 1 1, group 2 had 2 ones, and group 3 had 3 ones. Then we compared adjacent groups because there is a there is a possibility of finding combination which differ only by one digit, and based upon that we created a column 2 where we had a group 1 which only differ where we had terms which differ only by only one ones. Same method as it's the same phenomena and same fundamental which we applied to K-maps also, where we said that we can combine adjacent squares having ones. Now then we didn't combine group 0 and group 2 because we know that at least two terms are differing, so there is no point of comparing group 0 with 2 or 2 with 3. Then we compared group 1 and 2 and we came up with this set of common numbers with only one number difference, and then we compared group 2 and 3. After we looked at it, we again did one more iteration where we compared group 0 and group 1 of column 2 because we had entries which were differing only by one number, right? So based upon this, we compared group 0 and group 1 and group 1 with group 2. We came up with these 6 entries, and if we do a further grouping, right, we will not be able to see any entry which differ only by one. So this is the end point for us. What we did as a next step was we eliminated the duplicate entries, right? And now what we have is we have number of terms with us, right? The first term is something like where we say that we have this entry, this is second entry, this is my third entry, and we have unused entries, this and this. Correct? So basically, if I have to write my function over here at the end of this day, right, what I can do is my function f is equal to 1, 5, 1 and 5 is nothing but a bar, c bar, d plus what is this particular 5 and 7? A bar, b, d plus what is 6 and 7? A bar, b, c, and one is what is 0189? We have one more term 0189, right? What is 0189? This is something called as b bar, c bar plus what is 08210? 08210 is nothing but b bar, d bar plus what is 2610 for? This is c, d bar, right? So this is our circuit at the end of the day. So just to mention it clearly again, right? How many terms we had pending over here? So basically, just to make it more clear, right? Let me use one more in color. We had how many entries remaining? 0189, which is nothing but b bar, c bar. This is nothing but b bar, d bar. This is nothing but c, d bar. Similarly, this is a bar, c bar, d. This is a bar, bd. This is a bar, bc. Correct? We have got 6 terms, and at the end, our final circuit is, and final equation for this circuit is this particular function, right? A bar c bar d plus a bar bd plus a bar bc plus b bar c bar plus b bar d bar plus c d bar, right? But if you see, right, right? If we let's do one thing. Let's try to put a k map for this function all together, right? And let's see if this is the minimal function or not. What I will do is I will copy this code in the next file where we obtained one function using a Quine McCluskey method, which is equal to a bar c bar d plus a bar bd plus a bar bc plus b bar c bar plus b bar d bar plus cd bar, right? So now if I draw a k map for this circuit, right? If I draw a k map for this circuit, I will end up, if I have to draw a k map for this particular circuit, right? What I will end up getting is, right? This is a circuit which I will obtain using k map for this particular expression, right? And is further minimization for this circuit possible if we do use k map, right? Yes, it is possible. If I use this as one, this is second, this is third group, right? If I use k map for this circuit, my function f would be equal to what? A bar bd plus cd bar plus b bar c bar. So basically, the purpose of looking at this is Quine McCluskey method, right? Method. It gave us a circuit. We got a circuit. We were able to look at okay, what this circuit will be comprising of, but we have not yet done circuit minimization because KMap is able to do circuit minimization further for us. So we were able to look at minterms. We were able to reduce the circuit, but it's not the minimum possible circuit, right? So basically for this, what we need to do is we need to have a method to eliminate basic redundant terms which are present in Quine-Mikulski solution, right? For this thing, what we will do is in the Quine-Mikulski method, we will do something called as a prime implicant chart, PI chart. Okay. The prime implicant chart is the second part of the Quine-Mikulski procedure. It is used to select a minimum set of prime implicants. Similar to the Carnot map, we select the essential prime implicants and then we select enough prime implicants to cover all the minterms of the function. So I hope this is clear, right? So basically, just to recap, what we did in Quine-Mikulski method is we did a grouping. We figured out entries with a consecutive entries with only one digit being different, and with only one digit being different, we were able to reduce the entire function into set of six expression, and we created a circuit of those six expression. Now if you see, this particular expression is definitely a minimized version of the initial minterm expression which we had, where we had like 10 terms. Eventually we were able to obtain a circuit with only six terms, in the six terms getting odd and number of literals being less in each of the term. But this is not the effective and most minimized circuit possible. What we got through this step of Quine-Mikulski method is all the prime implicants, right? Now we have to do, what we have to do is we have to look for the essential prime implicants, and then we have to just eliminate the ones which are not at all required. For doing this, right, what we do is we do something called as a prime implicant chart, and let's understand prime implicant chart over here. So let me title it as prime implicant chart. And if I put our function again, right, our function was something like, our end solution was 0189, which was something like b bar c bar. Then we had 0 to 810. So I'm just carrying it forward from the previous discussion. We had b bar d bar. Then we have 2, 6, 10, and 14 cd bar. Right. So basically, this is what I am carrying over from this particular file. Right. And then we had something called as, next item was 1 and 5, which was nothing but a bar c bar d. Then we have a bar bd, which was nothing but 5 and 7. And at the end we had like 6 and 7, a bar bc. So what we can say, we can simply say all these were prime implicants, and we were able to find all the prime implicants using Quine McCluskey method. What we have to do is we have to now find the essential prime implicants, and we need to have a technique for that. So what we do is we will convert this into a chart. In the y-axis we mentioned all the prime implicants, and on the x-axis what we will do is we will mention all the minterms we had in the beginning. We had 10 minterms in the beginning: 0, 1, 2, 5, 0, 1, 2, 5, 6, 7, 8, 9, 10, and 14, right? So basically we have 10 terms over here. Now 0 is found in first term, it's found here also. Similarly 1 is found in this term, it is found here as well. Similarly 2 is found here, it's found here. 5 is found here, here. How about 6? 6 is here, and at the bottom 7 is here, here. 8 is what? Second. 9 is where? First only. 10 is where? In this expression. That's it. And in this expression as well. And where is 14? In third expression, right? Now what we have done is we took initial minterms, whatever we had, we mentioned them as part of our x-axis over here. This is the initial function we had, and this is number of prime implicants, basically all the terms which we got by circuit minimization. Now what we are saying is we can minimize this circuit further, and to do that, right, what we did is we created a prime implicant chart, and what we have to do now is we have to look for minterms that are covered by a single term only, right? Now how many entries are there which are covered only by single term, right? If you have to look what all is covered by a single term, 0 is covered by 2 terms, 1 is covered by 2 terms, 2, 5, 6, 7, 8, 9 is covered by 1 term, and 14 is covered by 1 term. This is clear, right? Now once a term is included in the solution, so basically simply it means that we need to have a term. So basically it simply means that we definitely need to have this term in the final expression, right? Similarly we need to have this term in the final expression as well, correct? So basically these are the minterms which we will cover if we are including this particular term. Now since we have already, if we are including these particular terms, it means, right, okay, so just to reiterate, right, what we did was we saw what all minterms are covered only in one of the equation. 9 was covered in one equation, 14 was covered in one equation, and what we did is we said that since they are covered only one equation, we definitely need to have this equation in the final solution, this equation in the final solution, right? If we included this term, right, 6 is already included, so this particular things become redundant, this becomes redundant because 2 is also covered, 10 is covered, this will also become redundant. Similarly if we have included the first term, so basically 8 is included, so this is becomes redundant, 1 becomes redundant, 2 becomes redundant. Now what is left, right? We have only left with these two things like 1 5 and 5 7. Now tell me one thing, if we simply include these two terms together, right? So if we include one term a bar bd, these two should also be covered, and we have a solution with us, right? So this is a strategy we use, and what we can simply say is our function f of a b c d is nothing but b bar c bar plus cd bar plus a bar bd, and this is a solution which we got by maps as well, right? So I hope this is clear. This is a bit confusing in the beginning, right? And but what we can do is, I think I should reiterate it once. The step was simple. We just did a grouping of minterms depending upon number of ones in the minterms, arrange them in the ascending order. Then we compared adjacent groups, and we kept on comparing the groups till the time we had only one change, right? And we reached to a situation where we had set of prime implicants where we said, okay, these are the terms and we can't reduce any further. We were left with 6 terms, and this was the operation. Then using a K-map, we saw that even though we were able to reduce the circuit, minimize the circuit from 10 terms to 6 terms, and with product literals being less, we have a problem here that this is not a minimal circuit, and KMF was able to give us a better minimal circuit. Then we looked at the second part of Quine McCluskey method, where we said that okay, we have prime implicants, and we did do a prime implicant chart where we said okay, B bar, C bar, P bar, D bar, all the 6 terms which we were able to drive using Quine McCluskey method, we plotted them, and then we plotted all the min terms which are there in the solution, which were there in the question in the beginning. And then we did a one basic thing, like we looked for all the terms which are covered only once, right? The term which are covered only by one term. 9 and 14 were covered only by one of the terms, right? Since 9 and 14 were covered only by one of the terms, we definitely need to have those terms as part of our final solution. And when we did that, right, we were able to cover 0, 1, 8 and 9. And since we covered 0, 1, 8 and 9, we were able to eliminate other midterms where we don't need those particular things, right? Similarly, for 14 we were able to draw a chart and eliminate the remaining midterms, and then essentially at the end we were left with these two entries. And what we saw is, if we pick up this term A bar, B bar, D, which is like these two things, we can eliminate these two as well, and this is our final solution. So, and usually it's like if you practice more questions on this particular topic, it will become more clearer. I hope this was helpful and I tried to explain this in depth. Hope you like this lecture, and stay tuned for the future ones.